Hey everyone! Today we're diving into one of the most exciting breakthroughs in robotics this year. NVIDIA just released GR00T-N1, a foundation model for humanoid robots that can perform complex manipulation tasks with remarkable intelligence and adaptability. If you're curious about how robots are becoming more like humans in their ability to understand and execute tasks, stick around, because this is genuinely revolutionary.
Let me set the stage. For decades, robots have been locked into repetitive, scripted behaviors. They're great at doing the same task 1,000 times in a factory, but ask them to do something slightly different and they're lost. The core issue is that robots need to be generalists, just like humans. You don't get retrained every time you encounter a new task. But here's the catch. Training robots on real-world data is incredibly expensive and time-consuming. A human teleoperated a robot for 88 hours to collect what NVIDIA calls real-world data. That's extremely limited compared to the millions of hours of video available on the internet. This creates what researchers call the data island problem. You have robot data, human videos, and simulation data, but they're all separated. There's no large internet-scale data set of humanoid robots like there is for text or images. Enter GR00T-N1. The name stands for Generalist Robots for One-Off Tasks, and it's a Vision Language Action Model, or VLA for short. Think of it as three brains working together. First, there's a vision language module that sees the robot's cameras and understands language instructions. It's running on an NVIDIA L40 GPU at 10 Hz, so it processes information 10 times per second. Second, there's a diffusion transformer module that generates the actual motor commands at 120 Hz. That's 12 times per second for smooth, natural movement. Both modules are tightly coupled and trained together end to end. The brilliance here is architectural. The Vision Language Module is System 2 in the researchers' terminology, inspired by Nobel Prize winner Daniel Kahneman's concept of human cognition. System 2 is slow, thoughtful reasoning. The diffusion transformer is System 1, which is fast, intuitive action generation. This mirrors how humans think. We reason about what to do, then our muscles just execute it smoothly without conscious thought. Now here's where GR00T-N1 gets truly innovative, the data pyramid. Rather than treating all training data the same, NVIDIA organized it by embodiment specificity and quantity. At the base of the pyramid, you have massive amounts of web data and human egocentric videos. These provide broad visual and behavioral priors. In the middle layer, you have synthetic data generated from physics simulations and neural video generation models. At the peak, you have the real robot data, which is expensive but grounded in actual physics. This is brilliant because it mimics how humans learn. We watch videos, read descriptions, but ultimately our knowledge is grounded in physical experience. The synthetic data generation is where it gets wild. NVIDIA fine-tuned video generation models on their 88 hours of real teleoperation data, then generated 827 hours of synthetic robot videos, effectively multiplying their real data by 10. Imagine if you could watch 10 versions of every skill a human demonstrates. That's what they did. And it's generated with novel language prompts in counterfactual scenarios that capture possibilities that would be prohibitively expensive to collect in the real world. Let's get into the technical details. The vision language backbone is based on Eagle-2, a pre-trained vision language model with 1.34 billion parameters. The full GR00T-N1 2B model has 2.2 billion parameters total. When you give it an image and a language instruction, like pick up the apple and place it in the basket, the Eagle-2 model converts these into token embeddings at multiple layers of abstraction. They discovered that using the 12th layer instead of the final layer actually improved both inference speed and performance. That's a practical engineering detail that matters. The diffusion transformer uses what's called flow matching for action generation. Instead of predicting discrete actions, it starts with pure noise and iteratively refines it into smooth action sequences. The model predicts action chunks of 16 time steps at 120 Hz, which is planning about 130 milliseconds into the future. That chunk-based approach is inspired by prior work, but critical for getting smooth, realistic motion. The key innovation for handling multiple robot embodiments is elegant. They use embodiment-specific MLPs, neural networks with multiple layers, to project different state and action dimensions into a shared embedding space. A single-arm robot arm and a humanoid with two dexterous hands have completely different action spaces, but by embedding them in a shared space, the model can learn generalizable features across embodiments. For data sources that don't have action labels like human egocentric videos, NVIDIA trained a VQ-VAE model to extract latent actions. The VAE learns to encode the relationship between consecutive frames, creating a learned action space that's embodiment agnostic. They also trained inverse dynamics models, or IDMs, which predict actions from image pairs. This technique lets them turn actionless videos into training data by inferring what actions must have occurred. How does this compare to earlier approaches? Previous vision-language action models like RT2 also fused vision and language, but GR00T-N1's dual system design is fundamentally different. RT2 trained end-to-end with a single unified architecture. GR00T-N1 keeps vision-language processing and action generation separate but tightly coupled through cross-attention. This provides more flexibility. You can swap out the vision-language backbone without retraining the entire action model. It's more modular. The data strategy is also distinctly more sophisticated. Earlier work used real robot data, human videos, or simulation separately. GR00T-N1 code trains on all three simultaneously through a unified data pyramid framework. The use of video generation models to create synthetic training data at scale is genuinely novel. Prior work used text-to-image diffusion for data augmentation, but generating entire video sequences is a quantum leap forward. Regarding diffusion models for action generation, GR00T-N1 builds on diffusion policy and other flow matching works, but applies it in a multi-embodiment setting with heterogeneous data sources. The flow matching objective is more elegant than older denoising diffusion models because it treats action generation as learning a vector field rather than an iterative denoising process. Let's look at what this actually achieves. NVIDIA evaluated GR00T-N1 on 3 simulation benchmarks and real-world tasks with GR1 humanoids. In simulation on robo-CASA tasks, GR00T-N1 achieved 32.1% success rate with 100 demonstrations per task, compared to 25.6% for diffusion policy. More impressively, on the DEX MimicGen cross-embodiment suite, it hit 66.5% versus 56.1% baseline. On GR1 humanoid tasks, it achieved 50% success versus 32.7% for the baseline. The real-world results are more compelling. On real GR1 humanoid robots performing pick-and-place tasks, GR00T-N1 achieved 82% success rate with full data, compared to 46.4% for diffusion policy. Remarkably, trained on just 10% of the data, GR00T-N1 achieved 42.6% success, only 3.8% lower than diffusion policy with the full dataset. That's data efficiency in action. When they tested using neural trajectories during post-training, they saw consistent gains. On robo-CASA tasks with 100 demonstrations, adding synthetic neural trajectories improved performance by 8.8%. This validates that synthetic video-generated data transfers meaningfully to real-world performance. A particularly elegant demonstration was a pre-training evaluation where they asked the humanoid to place an object positioned to its left. The object was out of reach for the right hand, requiring a bimanual handover strategy. The pre-trained model had never seen this exact scenario, but achieved 76.6% success by spontaneously performing left-hand grasp to right-hand placement. The model had learned a generalizable strategy from the data pyramid without explicit instruction. So what can we actually do with this? The researchers demonstrated language-conditioned manipulation tasks on the GR1 humanoid. Beyond pick and place, they showed articulated object manipulation where the robot must grasp an object, place it in a storage unit like a cabinet or drawer, and close it. They demonstrated industrial applications like machinery packing and mesh cup pouring. The most complex example was multi-robot coordination, where 2 GR1 robots collaborate to complete tasks. The data efficiency is the key practical advantage here. Typically, training a manipulation policy on a new task requires hundreds or thousands of demonstrations collected by hand. GR00T-N1, with its pre-training on the data pyramid, learns effective behaviors from just dozens of demonstrations, which makes it actually feasible to deploy on new tasks without months of data collection. The model is also open source. NVIDIA released the GR00T-N1 2B checkpoint, the training code, and parts of the training dataset. This is remarkable because foundation models are typically kept proprietary. By open sourcing it, NVIDIA is essentially inviting the entire robotics community to build on this work. The researchers are honest about limitations. GR00T-N1 currently focuses on short-horizon tabletop manipulation tasks. Long-horizon tasks involving locomotion, like navigating to a different room than manipulating something, are beyond current capabilities. The synthetic data generation, while impressive, still struggles with complex physics like liquids and articulated object dynamics. Video generation models can hallucinate or create videos that violate physics. Future work aims to improve these aspects. The training requirements are also substantial. GR00T N1 2B used 50,800 GPU hours for pre-training. That's enormous compute. However, fine-tuning on downstream tasks is much cheaper. On a single A6000 GPU, you can fine-tune it with batch sizes of 200 on just the action and state modules, making it more accessible. GR00T N1 represents a genuine step forward in robotics. By cleverly combining vision language models, diffusion-based action generation, heterogeneous data sources, and a data pyramid strategy, NVIDIA created a model that genuinely learns to generalize. The data efficiency is remarkable, the dual system architecture is elegant. Most importantly, by open sourcing it, they're essentially inviting the entire robotics community to build on this work. This is the direction robotics is heading. Foundation models trained on massive heterogeneous data sources that can rapidly adapt to new tasks and embodiments. We're not there yet for truly general-purpose humanoid robots, but this is a substantial step forward. The bar has been raised for what's possible in robotic manipulation.
Thank you so much for watching. If you found this deep dive into GR00T N1 interesting, please hit that like button and subscribe for more videos on cutting-edge AI and robotics research. Drop a comment below if you have questions or want to see coverage of other papers. Thanks again.